In this third module of Chapter 7 on extensions of stable population theory, Module 7.3, I cover multi-regional demography. Rogers in 1995 is recognized as the pioneer of multi-regional mathematical demography, an area of demography concerned with the mathematical description of the changes in populations over time and space. This sub-area of demography, referred to as multi-regional demography, considers persons occupying different regions as being in different states and therefore in different populations, and it opens populations to the flow of persons among populations. He demonstrated that generalizing demographic concepts to multiple states was relatively straightforward, inasmuch as assuming constant birth, death, and migration rates, each region or state would eventually contain a regional share of the overall population, and the population itself would eventually converge to the fixed age by region distribution and a constant rate of growth. In the following section, I present three basic two-region models that illustrate the concept of multi-regional demography. These include two models not incorporating age structure, one in which the location is aggregated by birth origin and another in which location is disaggregated by birth origin. And then a third model presented here is structured by both age and location. Model 1, location aggregated by birth origin. The simplest population in which migration is considered consists of subpopulations without age structure in each of two regions. Let IA equal per capita in-migration rate for region A, OA equal per capita out-migration rate for region A, IB equal per capita in-migration for region B, and OB equal per capita out-migration rate for region B. Then BA and DA equal per capita birth and death rates for region A, and BB and DB equal the per capita birth and death rates for region B. Suppose that within one time period, the two regions experience the changes given as follows. The rates for region A are 0.2 births and 0.05 deaths and 0.30 outmigrants per individual residing in region A per epoch. The rates for region B are 0.1 births, 0.02 deaths, and 0.10 outmigrants per individual residing in region B. The appropriate equations for the numbers in each of the two regions at time t plus 1, denoted NAT plus 1 and NBT plus 1, are NT plus 1A equal NTA times 1 plus BA minus DA minus OA, and then plus OB times NTB. And NT plus 1B equal NTBA times 1 plus BA minus DB minus OB plus OA times NTA. These equations state that the size of the populations at time t plus 1 result from the increment owing to each region's natural increase, the decrement owing to each region's outmigration, and each region's increment owing to the in-migration from the other region. The results of model iterations through time 12 are given in table 7.5. Column 1 is time, columns 2 to 4 contain numbers, columns 5 contains growth rate, and columns 6 and 7 contain the percentage in regions A and B. Note that the percentage of the total population in each of the regions stabilizes at around 29% and 71% for regions A and B respectively. Overall, the growth rate approaches a constant rate lambda equal 1.1, which is also the growth rate that each of the two regions will eventually experience. This illustrates that this simple two-region model populations will eventually possess fixed regional shares at 29 and 71% and a single fixed growth rate equal 1.1-fold per epoch. Model 2, location disaggregated by birth origin. The preceding model considered only the number in each of the two regions without regard to whether the individuals were born in the region of residence or not. To disaggregate the individuals within a region into those that are native born and those that are immigrants requires modifications. Let A, T, B that's a superscript B, equal the number of individuals in region A at time t who were born in region B, where the superscript denotes the region of birth. Analogous terms are the following. The appropriate accounting relationship for the number of individuals in region A at time t plus 1 who were born in region A will consist of three components. The net number of individuals. This component results from the natural increase of individuals in region A who were born in region A and can be expressed as NATA times 1 minus birth rate in A minus death rate in A minus outmigration of A. And then 2, the net number of births by individuals in region A who were born in region B. This component is expressed as BA times NAT in region B, the superscript B. And then 3, the number of immigrants born in region A who, at time t, were located in region B. This component is expressed as OB times NBTA. The number of individuals in region A at time t plus 1 who were born in region A is equal to the number in region A at time t who were born in region A times 1 minus birth rate in region A minus death rate in region A minus the outmigration rate of region A plus the birth rate in region A times the number in region A at time t that were born in region B plus the outmigration rate of region B times the number in region B at time t who were born in region A. The number of individuals in region A at time t plus 1 who were born in region B is given by this expression. Note that because all births to alien migrants are added to the native population stock, this equation contains no birth rate. The analogous equations for the numbers in regions B at time t plus 1 are given by these expressions. An example projection is presented in table 7.6 using the same parameters as it used in the previous model, where the population was not disaggregated by birth type. Time in the first column. The next sets of 3 columns contain the number in region A by birth origin. The 3 columns contain the number in region B by birth origin. This column contains the grand total number of individuals in both regions, and the last column contains the 2-region population growth rate. Similar to the birth aggregated model, the percentage of the total population in each of the regions stabilizes. In other words, they are fixed regional shares. Unique to this 2-region population that is disaggregated by birth, this population will eventually possess fixed birth origin shares. In region A, for example, 21% were native born and 29% were born in region B. There is also a single fixed growth rate. The overall growth rate approaches a constant of 1.13, which is also the growth rate that each of the 2 regions will eventually experience. Age by region projection matrix. The general configuration of a transition matrix for a 2-region population with age structure is similar to a Leslie matrix in that it has a top row or rows and a subdiagonal of non-zero elements. However, each is partitioned into groups of 2x2 matrices whose elements serve as either the transition from age x in region A to age x plus 1 in region B, or a birth in region A to region A, where there is no movement. Where the top row of birth elements denote the number of offspring produced by individual age x in region A that stay in region A, the number of offspring produced by individual age x in region A that move to region B, the number of offspring produced by individual age x in region B that move to region A, the number of offspring produced by individual age x in region B that stay in region A. And subdiagonals denote the probability of surviving age class X within region A, the probability of surviving age class X from region A to region B, the probability of surviving age class X from region B to region A, and the probability of surviving age class X within region B. We use the following values for the matrix elements to project a 2-region population from time t0 through time t equal 5. The results of which are given here, including the top row reproductive rates and the subdiagonal rates, including the between-region outmigration rates A to B and B to A, the staying rates A to A and B to B. Although Region B has higher growth rates due to survival, migration from B to A generates larger populations in Region A. The results of the first 5 time steps of the projection, starting with a single individual in each age class for each region, are presented in Table 7.7, where the first column contains time, the next 8 columns the number by age in each region, and the last column the grand totals. The results show that the properties of stable theory emerge such that a stable age by region distribution is eventually attained with 62% of all residents in Region A and 38% in Region B. Additionally, the effect of growth within a region supersedes the effect of migration. For example, larger migration rates from Region B to Region A were swamped by the overall growth rate. The addition of age structure to migration models highlights the lag between migration and its manifestations of migrants via the birth and death rates. Keyfitz, 1985, commented that the matrix is like a building with a good mixing of air in each room, but little circulation between rooms. In other words, we can expect that after any disturbance, the within-room variation will settle down to the stable form more quickly than the between-room variation. A comparison of the population composition or structure output of the 3 multi-regional models shows that when there is no age structure, the convergence to fixed fractions in each region is monotonic or nearly so. When age is added, we see oscillatory behavior due to the age lags as the populations converge to stable age by region distributions. These graphs show that dimensionality increases geometrically with each new region, and thus illustrates why demographic analysis of multi-regional models is generally restricted to closed populations. This ends the 3rd module of Chapter 7 involving multi-regional demography.